Okay, guys, we're going to get to the next of our vector product quantities. It's going to be angular momentum. And just as we have our linear momentum, and we're going to go over linear momentum in just a sec, but just as all of our other translational motions have a rotational equivalence, so does momentum. And so let's start with linear momentum and take that where and go where that takes us. So we have linear momentum. Okay, and we have given it the value p. And it is defined, or Newton defined this momentum as mass, or the vector as mass times our velocity vector. And then if we take the time derivative of that to get for our force term, that dp dt, which equals force, by the way, okay, equals force, is equal to, we product roll this, so it's going to be dm, or dm dt times v, which we don't use very often, but this was the mass flow times the rate, times the speed of that's happening. This is, we talked about this with rockets and with rockets and with a hose, like with a fire hose, where the water's coming out so fast, and there's so much of it coming out so fast that there's a force pushing the other direction. And there's also our mass times dv dt, and this is our more traditional one because this becomes our acceleration times our mass, and that's what we usually know as Newton's second law here. But there are, of course, these have direct analogs, and for linear momentum we are going to call it L. L is our linear momentum. Okay, and L equals, now our analog for mass is moment of inertia, and our analog for velocity is angular velocity, omega, and this is our angular momentum, L times I omega. And those of you that are into tech companies and that sort of thing, that is where the term I omega came from, where they invented zip drives, and they were the first real purveyors of external portable storage. And so, what does this look like? Well, we're going to take, for example, well, hold on for a sec. Okay, well, I'm going to give you a demonstration of my favorite example of angular momentum, and it is given with an egg. And the problem is, how can you tell the difference between how can you tell the difference when an egg has been hard-boiled or is fresh? And so here's my example here. Here is an egg. It is a fresh egg. And you spin it. Okay, and let it go, and it will spin and spin and spin until it will eventually slow down because of the friction on the table. But the way to tell the difference is you give it an initial velocity. So you spin the egg and let it go, and maybe spin a little more, and spin it and spin it, give it a good, okay, get it going pretty well, and then I'm going to stop it and watch what happens after I bring it to a stop. See that? Let me try it again. See if you guys can see what we're doing here. Spin, 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 stop. Why does it do that? When I grab it, I don't give it another flick. I stop it. Okay, so why does it keep going? Well, this is a fresh egg, and because fresh eggs are not solid, they're liquid on the inside, you get the internal rotation of the yolk spinning And when you stop the egg, you're only stopping the outside of the egg. The insides still have some angular momentum, and it allows the egg to keep spinning. If you do that with a hard-boiled egg, it will stop the egg, and it won't spin anymore. So that's my favorite example of linear momentum. And now or of angular momentum. Now there are others. Imagine you have someone on roller skates, and because this is a perfect world, there's no friction or anything like that. But we're going to do a top view, and so you have a person. Okay, you've got a skater coming down, and she has an initial velocity in this direction. Okay, and there's a mass. She of course has a mass. But then once she gets to a particular point, there is a pole. And she reaches out and she grabs the pole to create a radius. And she goes out, she grabs the pole, and all of a sudden, instead of her traveling straight, she starts traveling in a circle. Like so. All right, and then she gets to a particular point. Let's say she makes it all the way around to here. All right, and at this point, she's going to have her momentum, her linear momentum, is going to be in this direction. Okay, so her P will still equal mv going in that direction. Okay, however, she will have experienced, in order to make this happen, she will have experienced a torque. And we know that our torque, because you remember torque, that if we have it's the force acting on a distance. And so if we do if we have a rotating rod here, and we have a radius to this point, let's say the force acts a little bit further in from, so that's R, and here's our F, that we're going to have a torque, and this is separated by this angle theta, and our torque is going to be R cross F, okay, with the magnitude being R F sine theta, and the direction of it is going to be, to here, it's actually going to be in k hat. It's going to be pointing up, up out of the screen at the axis of rotation. So it's pointing up this way for this. Remember our right-hand rule, because it's our R going this way, and then crossed into the F in that direction. So our thumb is the direction of our torque. So this would actually be, this would wind up being RF sine theta k hat would be our torque in this particular case. Well, down here she's going to experience the torque, and her torque is going to be, okay, well, we know her torque equals R cross F, but our F is dp dt, so this becomes R cross dp dt, or we can extend this operator out, but it's not really, it's not entirely this, because our D is I'm losing my train of thought here. Technically, it's not just dp dt, but usually our radius doesn't change. It would actually generally be d of ddt of R cross P. But usually our R doesn't change, and so that would just become 0. That would just 0 out when we do our product rule. Okay, so that would look like, that would look like this over here. So I'm just going to write it a little differently over here. That would equal R cross dp dt plus dr dt plus our momentum. But because R doesn't change, I'm sorry, times. But because this doesn't change, this goes to 0, and we have R cross dp dt. Well, yeah, and so this is constant, so that doesn't change, which gives us an angular momentum L that is defined as our radius crossed with our momentum. Okay, which also winds up being our radius times mv. Okay, which is also our angular momentum. Okay, now this brings us to, this is going to be a relatively short thing that this process carries out, and oh, sorry, there's angular momentum. This process does carry out like it normally does. That if you have a whole bunch of these particles, if we set our x and y axis here, and we rotate around this point, and we have a whole bunch of individual particles here. So we have a particle here, and a particle there, and a particle there, and a particle over here, and a particle in here, and this one has a moving that direction, this is moving that direction, it's moving that direction, and that direction, and let's go this direction. And all of these are going to have, if we added them all together, then our total momentum, L, okay, is going to be equal to the sum of the linear, the sum of the angular momenta of each one of these little dudes. Okay, and this becomes the sum of their radius crossed with mv I. And so our dl dt, if we take the time derivative of this is going to wind up equaling d dt of this whole sum right here, Ri, crossed with mvi. Okay, which of course, if we know our math, it equals that the torque, this is our torque, is going to equal, our torque is going to equal the sum of our individual torques about the system, which is what we've been looking for, and so that's our relationship between our angular momentum and our torque. Now, there is an unusual case, and this happens with objects that are not rotating can still have, rotating or revolving, can still have an angular momentum. And here's a situation where that happens. You have an object right here that has a momentum of mv. Okay, but you want to determine its angular momentum about a point that is off of the line. So we could have this point right here, and because as this travels, this is going to have a as it moves along, it is going to move through a change in theta, okay, and it's going to be at this distance. This winds up being we wind up having this here's our momentum, and this is our r, and so we get this, that's r continued, and so here would be the theta between our momentum and our r, and this would wind up being r mv sine of this theta over here would be the value of our angular momentum. And it would, however, change as we move past this point because our radius would be changing, and then we start getting some more complicated situations. But just know that this is what our L would equal for this sort of situation, and that it is possible for an object to have this angular momentum, even if it's traveling in a straight line, if it's being compared to this point. Which also brings up the issue that if we pick different points, then we're going to have different angular momenta. And so that is also a wrench that can be thrown into the works and a added difficulty to a problem that you guys may see. But that is about it for angular momentum, and I'm going to look for an example problem to give to you guys for our next lecture.